Hello there, Algebra 2 students. Mr. Weber here. Today we're talking about our second lesson in probability. We're going to talk about theoretical and experimental probability. Now that sounds really complicated, but it's not nearly as bad as it sounds. Trust me. This comes from pages 467 to 474, as well as 490 to 497 in your textbook. So make sure that you are looking at that resource if this does not make sense. As always, because this is a video, remember that you are welcome and encouraged to pause and go back and re-listen to something if you need to, and periodically to pause and try some stuff on your own, and then to go ahead and hit play. All right, let's go ahead and do it. You should have printed out the notes page for this. It'll make it a lot easier on yourself. So here we go. Probability is a measure of how likely an event is to occur. So think about some things that we typically use probability for. The chance that it rains, we express as a probability. The chance that you might win the lottery is a probability. It's the measure of a likelihood of an event happening. Okay, so each possible result of a probability experiment or situation is an outcome. Okay, so if we have a situation, whatever our desired outcome is, that is what we're going to try to measure. Okay, the sample space is the set of all possible outcomes. So let's think about this. If we want to keep it real simple, if you flip a coin, okay, and let's say you want to know the probability that that coin lands on heads, the outcome is the heads. The sample space is the total set of all possible outcomes. And if you flip a coin, there's only two outcomes. It's heads or tails. All right, so heads and tails would be the sample space, 2. And the outcome would be what you want, maybe heads, 1. Okay? All right, so an event is an outcome or a set of outcomes. In probability, we always express as a value between 0 and 1. So sometimes you see it as a fraction, sometimes you see it as a decimal, sometimes you see it as a percentage. But the point is, it's between 0 and 1. All right, so let's think about what we know about those two numbers. So if the probability is 0, what does that mean? It means that it is impossible for that event to occur. Not that it might not occur, it will not definitely ever occur. Okay? What about the probability of 1? So the probability of 1 means that you are guaranteed that it will happen. Okay, I would make a joke if we were in the classroom saying the probability that you have homework is 1. It's going to happen. Some of you are getting smart and saying, I'll do my work in class. I won't have homework. You still have it. You just did it early. Okay, here we go. Let's keep on going, rocking through these notes. Equally likely outcomes are outcomes that have the same chance of occurring. All right, so when you toss a fair coin, heads and tails are equally likely outcomes. What that means is think about what is the probability that it lands on heads. 1 out of 2. What's the probability that it lands on tails? Also 1 out of 2. So we would say that those two events are equally likely to occur. They are equally likely outcomes because their probabilities are both 1 over 2. 1 out of 2, 50%, 0.5. Does that make sense? Okay. Favorable outcomes are the outcomes in a specific event. This is what we're going to be counting. This is what we're going to be looking for. So if I roll a dice and I say, what's the probability that it lands on 5? That favorable outcome is the 5. If I say, what's the probability that I roll a dice and it lands on a number less than 3? Think about the numbers that are less than 3. It's just 1 and 2. Those would be my favorable outcomes, 1 and 2. Okay. For equally likely outcomes, the theoretical probability of an event is the ratio of the number of favorable outcomes over the total number of outcomes. So you're looking at what's happening in your situation, you're counting the number of favorable outcomes, the outcomes that you want, and you divide that by the number of total outcomes in the sample space, and that is your theoretical probability. Okay, you can see how it's going to almost always be in a fraction, which is a number between 0 and 1. Which you could also express as a percent or as a decimal. Okay, so the number of favorable outcomes, that's the desired outcomes. That's what you want. All right, and the number of the sample space, that is the total outcomes. So it's like your desired outcomes over your total outcomes. That's the heart of theoretical probability. Just understanding what are you looking for and what's the possible things that could happen. And if you know those two things, you can calculate your theoretical probability. Okay, let's try some. Okay, so here we go. Each letter of the word probable is written on a separate card. The card's placed face down, mixed up, and the card is randomly chosen. What's the probability that the selected card has the letter P? Well, the first thing is, let me show you how we're going to write this. So this looks, I know, a little bit weird, a little bit like function notation. Okay, so this big P on the outside, this always stands for probability. All right, so what this means is we're looking for the probability. All right, the P on the bottom, this represents our favorable outcome, which is what we're looking for. All right, and what is our favorable outcome? The letter P. So this is why there's P's on the inside. So if you see this, you can quickly know capital P means we're talking probability. What's inside the parentheses is what we're looking for. We're looking for the letter P. All right, so let's think about what is the probability that this we randomly select the letter P from all of these letters. Well, first off, we need to know that it's going to be a fraction, some way, shape, or form. It's going to be a fraction. So let's think about what's our sample space. All right, so how many total letters are there? Well, if I count those letters up, that's a total of 8 letters. All right, so 8 is going to be my denominator. Now, how many of those letters are a P? Only 1. So the probability that I select a letter P would be 1 over 8. Done and done. Okay, look at part B. What's the probability that we selected card has the letter B on it? Okay, so now we're trying to find the probability of a B. Notice the P on the outside, that stands for probability. It's always going to be capital P, always, 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 always. What's inside the parentheses will change based on what we're looking for. Now we're looking for the letter B, so we put a B on the inside. All right, so it's going to be a fraction. Has the number of letters in the bag changed? No, let's assume that we took the P from our first trial and we put that back in. Okay, so there's still 8 letters. Okay, now, how many B's are in the bag? Well, there are 2 B's in the word probable. Okay, so there should be a 2 on top. It's a B here and a B here. All right, so our probability is going to be 2 over 8. And remember, it's a fraction. And if that fraction can simplify, then you need to simplify it. So 2 over 8 can simplify to 1 over 4. All right, so that's our probability, 1 over 4. All right, you want to pause it and try to do C and D on your own? That'd be great. All right, C. What's the probability that the selected card has the letter C on it? Probability that we get a C. All right, still going to be a fraction. Still 8 letters in there. How many of those letters are a C? I don't see any of them. Oh, that was good. All right, so there are no C's in the word probable. That means that the probability is going to be 0 out of 8, or we would just say 0. All right, so it's impossible for me to draw the letter C if the only letters in there are the ones in the word probable. Just not going to happen. Okay, look at D. Now we're trying to find the probability that the selected card has a consonant. I know some of you are out there saying, I don't know what a consonant is. All right, so there are consonants and there are vowels. Your vowels are A, E, I, O, and U. If it ain't one of those, it's a consonant. All right, so the consonants are ones that are not vowels. Okay, so still going to be 8 letters. Let's look for our consonants. P, R, B, B, and L. Those are our 5 consonants. All right, so there's 8 total letters in the bag. Only 5 of those would be a consonant, so the probability is 5/8, and that's it. You know, unless it tells you to convert it to a decimal, if it were me, I would always represent probability as a fraction because it's just easier. You're thinking about the number of total on the bottom, you're thinking about the number of favorable outcomes on the top, and you're done. Okay, so unless it says to convert it to a percent or a decimal, I wouldn't worry about it. I'd leave it as a fraction. Okay, here we go. Number 2. A number cube has each side being 1, 2, 3, 4, 5, or 6 on it. That's a die, and it's rolled. What's the probability of rolling a 6? Okay, probability that I get a 6. Okay, so it's going to be a fraction. There are 6 possible outcomes, so 6 will be my denominator. And how many of those outcomes are a 6? Only 1. So the probability is going to be 1/6, done and done. Okay, let's look at B. The probability of rolling a 10. Okay, so the probability that I roll a 10. Still going to be a fraction. Still 6 outcomes. Now, how many of those sides have the number 10 on them? 0. So your probability is 0. Okay, does that make sense? I hope this is pretty straightforward. All right, what's the probability of rolling an even number? Here's where you're going to have to know what an even number is. So 2, 4, 6, 8. All right, so how many even numbers do we have? 2, 4, and 6. There are 3 even numbers. Total of 6. 3 are even. The number's 2, the number's 4, and the number's 6. Even, even, even. 1, 2, 3/6. Remember, if you can simplify, you do simplify. 1/2. Done and done. Are you doing okay? All right, here we go. All right, so the sum of all of the probabilities in the sample space should be 1. All right, so the sum of all of the probabilities of the sample space, all of your possible events. So if you think about this, if you take all the possible events that are out there and you add them all up, that should equal 1. That should equal the total of everything out there. Okay, if you add up all the probabilities in your sample space and it's not 1, you made a mistake somewhere. All right, because you don't have the sample space. There's something out there that you haven't counted yet. All right, the complement of an event E is the set of all outcomes in the sample space that are not in E. All right, so this is the complement is a way of thinking about the opposite, or some people think negative, but it's not really negative. It's basically, if you're looking for, if I'm looking for the probability that it's not heads, when I flip a coin, I could take the probability of 1, everything, and subtract the probability that it is heads. All right, that's the idea behind the complement. All right, the probability that it's not E is equal to the total, which is 1, minus the probability that it is E. So if I take away what is E, what is left is not E. Okay, so a way of doing that is, let's look at our sample space here. Let's say we have some probability up here, and we'll call this E. So we have the probability that we are in E and the probability that we are not in E. If we are not in E, then we are somewhere out here. Okay, so the probability is 1 minus the probability of E. So minus the probability you're in this circle, that will give me all of this space here. 1 minus E would be all of this space out here on the outside. Okay, it's a little bit difficult conceptually to understand, but once you do, it's pretty easy to do in practice. All right, so here's an example, number 3. 25 students in study hall. The table shows the number of students who are studying a foreign language. Okay, so 6 people are studying French, 12 students are studying Spanish, 3 students are studying Japanese. Okay, now here's the thing you have to understand. Not all 25 students in study hall are studying a foreign language. Okay, What's the probability that we randomly pick a student and the student is not studying a foreign language? All right, so we want the probability that they're not studying a foreign language. So FL here stands for foreign language, not Florida. So not studying a foreign language. Well, this is equal to, because of our complement rule, it's equal to 1 minus the probability that the student is studying a foreign language. All right, so if we can know what the probability that it is, if we can figure out E, then it's easier for us to calculate what's not E. Okay, 1 minus. So let's figure out how many students are studying a foreign language. So it's going to be a fraction here. I know there's 25 students in study hall, so that's my sample space. That's my bottom number. Now, how many students are actually studying a foreign language? Well, let's just add up those numbers. 6 plus 12 is 18, plus 3 is 21. So 21 students are studying a foreign language. Okay, so 21 over 25, that's the probability that a student is studying a foreign language. So what I want to know is what's the probability that they're not studying a foreign language. So I'm just going to do 1 minus 21 over 25. Now, if your calculator is really good at fractions, you can grab your calculator and do this. But I don't think you need it because this is really, really easy. I hope that you remember from a previous lesson when we talked about 1, the number 1 is kind of like a wild card because you can turn that into anything you want. I'm trying to change my pen color here and I can't find my mouse because it's so thin. Here we go. All right, so remember 1 is like a wild card. So instead of writing the number 1, I'm going to write this 1 with a denominator of 25. Well, if I want it to be 1 still, then all I need is the numerator and the denominator to be the same. 25 divided by 25 is what? 1. Okay, so I'm going to rewrite 1 as 25 over 25 because now I have the same denominators. I can just subtract the top. 25 minus 21 equals 4. So 4 over 25, that's the probability that a student selected at random is not studying a foreign language. Does that make sense? We started by finding the probability that they were studying a foreign language, and then we just subtracted 1. Okay, let's keep on going. Okay, in a standard deck of playing cards, the probability of drawing an ace is 1/3. Find the probability of not drawing an ace. All right, so the probability of not drawing an ace, that's going to equal 1 minus the probability that you do draw an ace. Well, what is the probability that you do draw an ace? They told us that. It's 1 over 13. So this is going to be 1 minus 1 over 13. All right, remember, let's just change 1 into a fraction that makes sense for us. 13 over 13. 13 minus 1, 12 over 13. And there's our answer. Done and done. Okay? All right, look at 5. 2 parts to this, A and B. All right, so each of the letters of the alphabet are written on a slip of paper and placed in a bag. The bag is shaken and 1 slip is drawn at random. What is the probability the slip of paper chosen has an A, D, R, or T? Okay, so we're looking for the probability of an A, D, R, or T. All right, so it's going to be a fraction. All right, how many letters are in the bag? Well, we put each of the letters of the alphabet, so that should be 26. So far, so good. Now, how many letters are in our favorable outcome? How many letters would be a favorable outcome, would be a success? Well, we're looking for the letters A, D, R, or T. That's 4 letters. All right, so our probability would be 4 over 26, but that's a fraction that can be simplified. So it's 2 over 13, divided the top and the bottom by 2. There's our probability. So the probability that I randomly select an A, a D, an R, or a T is 2 over 13. Okay, now what's the probability that the slip of paper chosen does not have that A, D, R, or T on it? Okay, so remember the probability that it's not A, D, R, or T is equal to 1 minus the probability that it is an A, a D, an R, or a T. Okay? So what is the probability that it is an A, a D, or R, or a T? Well, we just found that. That's from our previous part A. It's 2 out of 13. So we're looking for 1 minus 2 over 13. All right, so let's change 1 into something that makes sense for us. 13 over 13. 13 minus 2, 11 over 13. Change that to a fraction. I'm sorry, it is a fraction. That's our answer, 11 over 13. That makes sense? Are you guys with me? Okay, we're doing good. Just a couple more. All right, now let's talk about a little more vocabulary. All right, so we can estimate the probability of an event using data. Okay, so some of these probabilities we know what the theoretical probability is. But others, it's hard for us to know every single possible outcome. We don't know what all the possible outcomes are. So what can we do? Well, one thing we can do is we can model it by doing an experiment. Okay, we can look at some data and see what happens and use that data to estimate the probability of the event. All right, so in an experiment, each repetition is a trial. All right, the sample space of an experiment is the set of all possible outcomes. And the experimental probability of the event is the ratio of the number of times that event occurs over the number of trials. Okay, so here we go. This is a different type of probability. This is experimental probability. What we just talked about was theoretical probability. Experimental probability is slightly different. It's still thinking about desired outcomes over total outcomes, except that in an experiment, you're doing trials. Okay, so the number of trials is your sample space, the set of all possible outcomes, the number of trials. And the desired is the number of times that the desired event actually did occur. Okay, so here's a helpful way of thinking about it. Let's look at theoretical probability versus experimental probability. Theoretical probability is what should happen, all right, what we expect to happen, what should happen. Experimental probability is what actually did happen when we performed some experiment, when we gathered some data. Okay, let's look at a simple example of flipping a coin just because it makes sense. Obviously, this is not something you would do and build an experiment around because it's pretty easy for us all to look at and figure out what the theoretical probability is. Really, the reason you would want to think about or use experimental probability is because what you're looking at is so complicated that it might be hard for you to theoretically figure out what that probability would be. All right, so it's easier to kind of see what's actually there. All right, so let's look at this as a simple experiment. So theoretically, if I flip a coin, what should happen? Well, I know that the coin has two sides. One side is heads and one side is tails, right? So the probability that it lands on heads should be 1 out of 2, and the probability that it lands on tails should be 1 out of 2. That's because a coin only has two sides, and one side is heads and one side is tails. Are we good there? Okay, I hope so. Now, let's look at experimental probability. So in experimental probability, we don't know what the theoretical probability is or should be, so we do an experiment. Let's say that to make it simple, I flipped a coin 4 times. All right, so here's my results. Grabbed a coin, I flipped it. The first time I flipped it, it landed on tails. The second time I flipped it, it landed on heads. The third time it landed on tails, and the fourth time it landed on tails again. Okay, so now let's calculate the experimental probability. The experimental probability is based on the data of our experiment. It's based on the data of this outcome, not the coin itself. All right, we're looking at what actually did happen. Okay, so what's the probability that I get a heads? Well, I only got a head The coin only landed on heads one time out of those 4 trials. So the number of trials is our denominator. That's the total number of times that we did this experiment. The numerator is what our favorable outcome was. So it only happened one time. In trial number 2 was the only time I got heads. The probability that I got tails was 3 out of 4. All right, trials 1, 3, and 4 all landed on heads, and I only did 4 trials. All right, so did the probability of flipping a coin change? No, it didn't. The difference is one was theoretical, what we expect to happen, or what we think should happen. The other was experimental. What did we actually do? We gathered some data, and it's built, the probability is always built off that data. Okay, what you need to know is that if you want your experimental probability to be equal to your theoretical probability, you need the number of trials to go really, really big. All right, so the more trials you do, the closer your experimental probability should be to your theoretical probability. All right, so I only did this 4 times. If I were to flip this coin 4 million times, then it might not be exactly 2 million heads and 2 million tails, but that probability of heads and of tails should be close, really, really, really close to 1/2. Does that make sense? I hope so. If not, you can always reach out to me or one of your own teachers. All right, so here we go. If it's experimental, they will always give you data. So if you're not sure, is it theoretical or experimental, if they give you data, it's a good bet that it's experimental probability. All right, let's look at some examples. Students in a math class spin a spinner shown 50 times. The results are shown in the table. Use the data from the table to find each probability. Ding, 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 ding. That's experimental probability. Use the data from the table to find each probability. All right, A, what's the probability of spinning a 3? All right, so I want the probability that I spin a 3. I need to know how many times did I spin the spinner? 50 times. If I take the number of occurrences and add them all up, and I always do this just to make sure that I don't have a mistake in my data. So they told me that this was spun 50 times. If I wanted to make sure, I would just add 6 plus 11 plus 19 plus 14. That should give me 50. All right, so I want the probability that I get a 3. Okay, so how many times did a 3 occur? 19 times. That's 19 over 50. And that's my answer. Done and done. All you do is look it up from the table and put it over the total. Yes, that's it. Just remember, if you can simplify, you need to simplify that fraction. All right, look at B. What's the probability of spinning a number greater than 2? All right, so I'm with the probability of spinning a number greater than 2. I used x here just to put a variable in there. So the probability that x is greater than 2. Now, what numbers are on the spinner are greater than 2? 3 and 4. You need to be careful not to use the actual number 2. This didn't say greater than or equal to 2. It just said greater than 2. All right, so that means we have to be looking at the outcome of 3 and 4, and that's it. All right, so 19 plus 14, that's 33. So 33 over 50, because it still only spun 50 times. That's our probability. Ta-da! Does that make sense? I think there's one more example. If you want to pause it and try it on your own, that would be terrific. Otherwise, I'll just go ahead. Okay, students randomly chose one card from a complete deck of cards 26 times. The suits of the card was recorded and the card was replaced before the next draw. The results are shown at the table. So the card was replaced before the next draw. That's important because that means that every time we draw, there's still 26 cards. Okay, so the probability is not changing as we're drawing these cards. That would be complicated if it did change. Yeah, we might talk about that down the road, but not today. All right, so the probability is not changing. Here's our outcome. I were to add these up, 5 plus 9 plus 17 plus 5, that should be 26, and it is. All right, so what's the probability of getting a card from the suit of diamonds? So the probability of a diamonds. So let's go find diamonds. Where's a diamond? Oh, sorry, 26 times. That's the total number of times we drew a card. So that's the denominator. How many times did we get a diamond? 9 times. So what's that probability going to be? 9 over 26. Done and done. Okay. Lastly, B, what's the probability of getting a card that is not a club? All right, so how do we do a not? Probability of not a club. That's the same thing as 1 minus the probability that it is a club. So here's where you can really see that the complement, how it works and how it can be helpful. I could go ahead and add hearts and diamonds and spades. That's fine. I could do that. But it's a lot easier to look at the clubs and then just subtract it from 1. All right, so what's the probability that it was clubs? All right, so we're still taking it 26 times, but it was a club only 7 times. So that probability should be 7 over 26. So I'm looking at 1 minus 7 over 26. And let's go ahead and change this number 1 to something that makes sense for us. What do we want the denominator to be? 26. So let's make it 26 over 26. 26 minus 7, 19 over 26. That is our answer. Done and done. Okay, does that make sense? Hopefully it is. Today's lesson was about theoretical probability and experimental probability, but I hope that this makes sense. If it doesn't, please reach out to your teachers. We are here for you. You guys are doing great. Just keep up the good work. All right, you guys have a great day.